All right, good afternoon, everyone. Thank you for joining us for this session. My name is Brian McGraw. I'm a Senior Solutions Architect with AWS. Just wanted to remind you of a few things. Emergency exits in case you need them are on either side of the room here. Restrooms are outside down the hall. If you've had a chance to download the app, I want to remind you that at the end of this session to complete the survey. And last but not least, if you have a cell phone with you, we do ask that you put it to silent, just so we can kind of maintain the room and have a good experience for everyone. So with that, I'm going to introduce Mr. Joe Flasher to the stage to introduce the rest of our speakers.
All right, hello everyone. So I'm Joe Flasher. I'm the Open Geospatial Data Lead here at Amazon Web Services. And what this means is that I work with a lot of our customers across public sector and commercial sector and globally to help them work with geospatial data in the cloud. And I'm just going to take one brief minute here and tell you why I'm so excited about this session. So I'm on the open data team. We work with a lot of customers figuring out how to best work with open data, and I focus on geospatial. We also have the public data sets program through which we make high value data available in the cloud so that groups can innovate faster on top of large data sets. So the reason why I love ESIP so much is because they do the same thing. So they make my job way easier, so thank you very much for that. And so I'm glad to have them here today and talking to you about what they're doing. And the other thing that I really like is that in true Amazonian fashion, Andy's going to talk in a bit, but then she also has some of ESIP's users, some of their users, up here to talk to you about what they're doing. So Matt and Amanda will also be talking in a bit as well. So that's all I have. I'm just going to step off, and Andy, if you want to take over. Thank you.
Okay. All right, thanks everyone, and welcome to the what I believe is the last session of the day. My name is Annie Burgess. I am the lab director for the Earth Science Information Partners, or ESIP. Thanks to Joe for that introduction. My background is in remote sensing and snow hydrology. But for those of you who aren't earth scientists in the room, and a show of hands, who would not consider themselves an earth scientist, great. That means a lot of learning will happen. I guarantee that data collected by the earth science community has touched your life, probably today. You may have checked the weather this morning. You have an acute understanding if your home will be impacted by a natural hazard, a flood, an earthquake, a landslide. And you have confidence that the water you're drinking here in this convention center and the air you're breathing is safe. But what connects us more generally, and why we're all probably here today, is that we're faced with collecting, managing, and analyzing ever-increasing volumes of data. And we want to create actionable insights from those data, and they're probably housed across multiple agencies and a number of different formats. So today, I'll be talking about challenges and opportunities related to big earth science data. You'll also, as Joe said, hear from two additional individuals, Matt and Amanda. They've both been funded through the ESIP lab and have leveraged AWS Cloud research credits to solve their scientific challenges. Matt will be talking about real-time quality control for IoT data, and Amanda will be talking about using CubeSat data and machine learning to improve snow-covered area measurements. But first, let's get back to talking about the data. Understanding Earth dynamics are critical for multiple reasons. Revealing and mitigating the impacts of human-caused climate change, ensuring responsible and productive business enterprise, and improving global quality of life. And in light of this need, the research community has responded. We have increased the resolution of large gridded data sets. There are proliferation of streaming sensor networks, and the volume and variety of sensor types has increased. This is a really good thing. It means that scientists now have the opportunity to analyze petabyte-scale data. However, until recently, the power to analyze this data has been in the hands of relatively few. I think we can remember back to a maybe previous job or in graduate school where HPC was housed in a single department. In my case, it was across the street in atmospheric science, and we all just had to be jealous of our friends that had that compute. And of course, why we're all here is we've realized that AWS is providing a critical part of the solution to the big data challenge when it comes to both management and analysis. But most importantly, any agency, institution, or individual has access to the same infrastructure. But beyond big data, researchers are also able to accelerate the research process by using the cloud, especially if they're taking advantage of cloud-native data and elastic compute, similar to what is available in the program Joe was talking about with AWS's Open Cloud Data Initiative. The reality, though, is that advancements in science require integrating data from multiple sources. No one agency or institute collects all data to understand Earth's complexity. Scientists must find data across disparate archives and bring them together to make them actionable. And this means data must be interoperable. But creating interoperable data, can also not be solved by one institution alone. It's kind of contrary to the entire notion of interoperability. Therefore, I'd argue that research acceleration in the cloud is not as much of a technology challenge as a community challenge. And I've been excited to kind of hear session after session already this early in the conference echoing that sentiment of this kind of community or collective challenge. And that's where I see ESIP playing a major role. So ESIP, the Earth Science Information Partners, we're a nonprofit organization. We're a member organization, and we have about 1,000 active participants. We're funded by NASA, NOAA, which is the National Oceanic and Atmospheric Administration, and the US Geological Survey. ESIP members are software engineers, they're scientists that are managing and stewarding a vast, or maybe a significant portion of publicly collected Earth science data and information. ESIP members come together virtually and in person to share recommended practices around data stewardship. And this is particularly important and certainly relevant to why we're all here today, because our members, including our funding agencies, are rethinking and re-engineering Earth science data systems for the cloud. But we also believe that for scientists to fully utilize the volume and variety of Earth science data that will soon become available, it needs to be a landscape that they can navigate and innovate within. And the catalyst for that innovation within our community is the ESIP Lab. We provide technology development grants to Earth scientists eager to explore emerging technology. We encourage and assist those projects to build cross-disciplinary teams of end users and engineers to work together. And that cross-disciplinary nature improves the likelihood of additional funding for their projects and reuse potential within our community, because their projects are being developed within this community ecosystem where they can receive feedback early and often. So really, AWS Cloud research credits are fueling this dynamic technology development environment. And we've been able to provide more support to our members because their cloud costs are covered. And I would argue that those AWS Cloud research credits, their potential for collective impact is greater because they live within, let's see, I don't have a pointer, but they live within this ecosystem rather than kind of the spoke model where they would be going to any one of these individual institutions. All this to say that Earth scientists have recognized the power of big computing for quite a while. But by AWS democratizing access to the cloud And efforts like the ESIP lab, where we're encouraging earth scientists to get in and experiment with developing technology, we've created a framework that has the potential to provide cloud-savvy data stewards and scientists across all disciplines. So next you're going to hear from Matt Bartos and Amanda Tan. Matt will start off by talking about his project that he's involved with, Real-Time Sensor Testbed. I'd encourage you just to take a moment to look at the collaborator list for each of these projects and see kind of the variety of people that are involved in them. I'm also going to give a quick reminder that these projects are both funded over a 6-month duration and for less than $10,000. So really when I say grants, these are micro grants, but the lift that they get from the community development space, I think you'll be able to see that impact come through in what they present. So with that, I'll bring up Matt and turn off my volume.
Hey everybody, how's it going? My name is Matt Bartos, and I am a PhD candidate at the University of Michigan, where I study civil engineering. And my research focuses on the next generation of smart water systems. So what's a smart water system? Essentially, it's a system that uses real-time monitoring and control to improve the quality of service, to cut operation, maintenance, and construction costs, and also to prevent potential environmental and human health impacts such as combined sewer overflows, toxic algal blooms, and fatalities due to flooding. So a major focus of my research is a large-scale wireless sensor network for real-time flood monitoring in the Dallas-Fort Worth Metroplex. And you can see a couple pictures of our sensor network. We deployed roughly 40 sensors within the Dallas-Fort Worth Metroplex. And the goal is to monitor river stage, so the water depth, at the level of individual roadways. And in doing so, we hope to send targeted alerts to motorists to prevent them from driving into flooded roadways, to achieve better routing of emergency services, basically to ensure that we are not sending ambulances or other responders into dangerous areas. And perhaps someday, as connected and autonomous vehicles become more common, we'd actually like to be able to route traffic in real time around flooded roadways to avoid potential fatalities. And this is a really serious problem because in the United States, roughly 74% of flood-related fatalities are vehicle-related. They occur when people get stuck in crossings and they can't get out because there's flooding. So we built these wireless sensor networks. We built the cloud backend using AWS, using all the technologies we talked about at these sessions today. And surprisingly, the biggest challenge for us hasn't been the firmware or the hardware or the cloud backend or any of that stuff. It's ensuring that the data that we're providing to our stakeholders, so the people from the municipalities, from flood control districts, is both timely and reliable. This is not an easy problem to solve. So timely in the sense that if the data arrives too late, it's not going to be of much use to emergency management. It's not going to be of much use to providing alerts. At the same time, the data needs to be reliable. So essentially not too many false positives or false negatives. If you don't detect a flood event, that's a major problem. And if you detect too many false positives, that's also a problem because people will no longer trust your data. So to address these problems, we use this ESIP lab to develop a, we use this ESIP lab to develop a framework for real-time quality control and quality assurance of sensor data. It's essentially a specification for describing operations to quality control your data. And this specification takes the form of quality control recipes, which are documents that are specified in a JSON LD format that we describe in our project that performs atomic transformations on your data. These transformations are designed to be, one, human readable so that you don't need to understand a programming language to understand what operations are being applied to the data. Second, they're versionable so you can upload them to a repository and know the exact history of what's happened at the site. This is a major issue because when you're working with real sensor data, there's a lot of strange things that you wouldn't necessarily think happen. Like, for instance, like a tree might fall in front of your sensor, or your maintenance crew may move the sensor, introducing a bias into the rest of your measurements. And you need a format for accounting for all of those strange things that might happen that's not going to be taken care of by a one-size-fits-all algorithm. Finally, we want all of the steps to be reproducible and to describe the history of the sensor for improved data provenance down the road. So here I have just a couple of examples of these recipes. These are just tiny screenshots of much larger documents. But on the top there, in the top panel, you can see two time series, one in red and one in green. And these actually are from the same site. They're measuring water level over a bridge on a relatively large creek. And the top one you can see is almost unrecognizable. If you just saw that sensor stream coming in and you were from a municipality, you would probably say, get out of here, this looks terrible. But through a series of reproducible and atomic transformations, you can transform that top time series into the green time series underneath it. And that looks much more recognizable. It's just essentially a hydrograph occurring at this location. In the bottom example, I also show a simple application of this framework for machine learning. So you can use it to specify different classes of training data, training and test data, and you can use that to train a machine learning model. So in this case, I'm just training a simple two-class support vector machine to classify your hydrograph into base flow in red and a wave event or a storm event in blue, where the water level rises rapidly. So that could be very useful, for instance, if you are trying to detect flood events as they are occurring. You need something a little more complicated than a simple threshold test or something like that. Okay? So having implemented this, this framework for quality control, we apply it to roughly 60 sensor sites within the Dallas-Fort Worth Metroplex, the city of Ann Arbor. And we use AWS to disseminate this data to our stakeholders, so people from the municipalities and the flood control districts. So I'm not going to get into the architecture too deeply, but the quality control service is running on an Amazon EC2 instance. It digests these recipes and executes them and writes the data to an InfluxDB time series database instance that's running on the same EC2 server. Along with that, we are using a couple of well-known data visualization tools to make the data more accessible to our end users, including Grafana, which many of you are probably familiar with, and leaflet.js for mapping. In addition to that, we also have CORDS, which is a service being developed at the National Center for Atmospheric Research, which essentially is a tool for citizen scientists, scientists who may not be familiar with using cloud services for taking sensor measurements and visualizing them online. So our data is currently being used by a couple of stakeholders. Although this quality control framework is relatively new, it has had an impact so far. So in the Dallas-Fort Worth Metroplex, it's being used to calibrate a number of flood models that are being used by the cities in Dallas and Fort Worth. And it's also being used by the dam operators in the city of Ann Arbor. They've actually learned how to look at this data and figure out how to time releases from their dams in order to mitigate downstream impacts to aquatic wildlife, which I think is really cool. So with that, I'm going to hand it off to Amanda, who's going to show you some cool machine learning stuff.
So hi, everyone. My name is Amanda Tan, and I am the Cloud Technology Lead Developer for Research Computing at the University of Washington. And with the project lead, the ESIP project lead, Nicoletta Cristia, and a very talented biology, PhD in biology student named Tony Canistra, we've been lucky to work with ESIP on inferring snow-covered areas from high-resolution satellite imagery. So Snow is one of the most interesting and frustrating things to study as a hydrologist. What is amazing about snow is how dynamically it changes. You can see an area with snow in one place, but if you go to another place just a few minutes away, the whole dynamics change. And these changes in snow, both seasonally and spatially, affect a lot of ecological processes. And because snow is so sensitive to changes in climate, a long-standing question in scientific snow-related research is how do we actually identify these changes in snow? And in turn, how do these changes in snow affect a lot of the ecological processes? So it's kind of a chicken and egg situation. So for example, in this project, we are interested in studying snow and trying to identify how snow affects flowering phenology. And what flowering phenology is basically trying to understand the timing of when spring blooms happen up in mountainous areas. The picture on the right shows the relationship between snow cover and spring flowering. And you can see this picture on the right here. Actually, to my left, sorry. To my left, this picture closest here, you can see that there's snow here, but a few inches away, there's actually spring flowerings happen. And so the question becomes, how do we actually leverage the amount of data that's out there to identify these really, really fine nuances? If you see at the bottom right, this little chart there, this is the relationship between the disappearance of snow and the flowering phenology. And this relationship was actually derived from very painstaking observations, just like over a long period of time in a very, very small area. Then the question becomes, how do we actually get these kinds of relationship over areas that are much, much larger, right? And without having all these observation data. And the way that people have done it before is using satellite imagery. But the problem with satellite imagery is that a lot of times you don't get precisely what you want. You're limited either in space or in time. So this picture on the top, where you can see the little pink splotches, that is actually downscaled MODIS imagery, right? And you can see that the resolution is really coarse. And so if you're trying to get to identifying something that's shown in the picture, this kind of satellite imagery will not work. So what do we do? Okay, so let's just take a look at some of the current data sources out there, some of the satellite imagery sources out there. So on the top, you see that there's something called MODIS. And spatially, it's kind of coarse, it's 500 meters, but it's very good temporally. It's a near daily cadence. But on the other end of the spectrum, you have Landsat, which has very fine resolution, but it only goes around every 16 days. And then you have things like airborne LiDAR, which is basically planes flying over a certain area. And those come with very high spatial resolution and high temporal resolution, but they are really expensive to run. And they only fly planes over very specific areas. So this is where things get super exciting for me. Since 2013, we have had about 120 little satellites floating over the Earth, giving us, a view of the Earth at really, really high resolutions at 3 meters and almost daily. And so given all the complications, right, actually, I'm going to backtrack a little bit. So when we talk about those planet data, the problem with the planet data is that it's very limited in bands. And so again, we are running into problems with these different kinds of satellite products. So given all these complications, what can we do? We have hypothesized that we can try using the very buzzwordy machine learning techniques to derive snow-covered areas and fill in the gaps where data is missing. So for the purpose of this ESIP project, we're looking at a very small area in Yosemite called the Tuolumne River Basin, where we have actually ground truth data from LiDAR. And this is served to us via NASA's Airborne Space Observatory. And I will be referring to this LiDAR ASO data as ground truth data throughout the entire presentation. And what we need in terms of understanding hydrology or ecological processes is to derive something called a snow mask. And if you can see over on this far left side, those are what snow masks look like, the one in blue and the one in gray. And so the question is, how can we actually get snow masks from planet data? So our methodology, our overarching methodology is to first obtain the planet imagery data and to use ground truth data to train a convolutional neural network. The ground truth data is actually available as point cloud data, which we first convert to raster, and then we convert it to tiles. And then also for the planet data, it's available as raster data, which we then convert to tiles. So if you can imagine that both those layers should overlap so that we can actually see if we can get something meaningful out of the planet data. So next, using a convolutional neural network that's been trained with the ground truth data, we obtain a probability of snow versus no snow for an area. And then we derive a snow cover mask. So the blue, again, is a snow mask derived from the observed data, and the gray is what we're trying to derive from the planet data, which is actually the data from high-resolution CubeSat imagery. Okay. So where we are using AWS for our work is for storage and compute. We first download both the ground truth data and the planet imagery into an S3 bucket. Right now, the data is actually only about a terabyte, but we're anticipating that this data will actually grow. And I will touch more on this later in the presentation. We'll use the cloud-based platform known as Pangeo. There will be a talk, I think, tomorrow about Pangeo. But essentially what Pangeo is a Jupyter hub that you log on to. And in the back end, it uses things like Kubernetes and Dask to kind of parallelize your work. And so this allows us to process and run analysis on very large-scale data, if you can imagine. So the first thing that we want to do is to actually process all these raw files into something called cloud-optimized geotiffs. The benefits of cloud-optimized geotiff is it makes it for faster reading, that you can kind of just subset small little chunks directly. And so this enables us to compute where the data is stored. So you're able to actually run your computational with data directly sourced from S3. Okay, so after we actually, so what we use Pangeo for is for the tiling work, like I said before, we had to convert the rasters all the way into tiles, and then to process these raw files into cloud-optimized geotiffs. And then these process files are actually also then dumped back into S3 for the training and machine learning component. And you can see down here, the words might be a bit small. There's something, we use a machine learning algorithm called RoboSat, and we run this using Elastic Cloud Compute GPUs. So let me touch a little bit, just a very small bit on what RoboSat is. RoboSat has actually been developed by Mapbox, and it is an end-to-end machine learning pipeline written in Python to get feature extractions from satellite imagery. So it gives you that entire workflow all the way from data preparation, data extraction, getting the segmentation models running, and then eventually converting that result into something meaningful. So this is some preliminary results that we have from running our RoboSat algorithm, which is essentially backed by a convolutional neural network. And you can see that on this, the far right, which is the planet data, right, you can see that there's some white and pink specks there, which is actually depicting the snow. And you can see those gray blobs are, it could be rocks, it could be mountainous areas. And then in the middle, you can see the LiDAR-derived snow mask, which is actually the ground truth data. And if you look, you can squint hard enough, you can see little tiny green specks as well. But what we get out of this results is that actually the convolutional neural network predictions are doing really well, right? But what if we go on to something a little bit more complicated? So let's have a look at this. And this is actually showing an area where it's pretty forested. Again, the planet data is over on the far right, and then the ground truth data is in the middle. Here you can see that there's actually a lot of green areas, but the convolutional neural network, the model, is not capturing those areas. So what do those green areas actually mean? They're actually forested areas, but there is snow beneath the forested areas. What this tells us is that the model can actually capture snow cover when it's over a large open area, but it is not able to discern when it's the snow in between really small, tiny pixels in between trees. Let's take a look at another one of the results. And this is for snow areas versus lakes. And you can see that the lake on the planet imagery, you can see that there's a big gray blob right at the top right corner. And then again, that's the LiDAR-derived snow mask in the middle, which the lakes do not show up. And on this left here, you have the model. And the model actually does see that, okay, you know, lakes, even though it has some kind of reflectance, where we understand that it's not snow, but again, it's having a hard time with those little green spots, which are the snow under the forest canopy. So what are the next steps? I will touch a little bit more on that, but let's go on to the next slide here, which is how do we disseminate what we have done with ESIP and with AWS? And we want to make sure that as part of the ESIP deliverables that everything is open source. So all these algorithm and code are available in the GitHub repository, and all the training data and all the results will be maintained in a publicly available Amazon S3 bucket. And the data, as it grows and as it gets older, it will be eventually moved to Glacier. And all the model setup and compute environments, they will be kind of dehydrated into a Docker image and an Amazon machine image. And we will keep this using ESIP funds for up to 3 years so that anybody who wants to try using this can actually have access to it. But the next steps for us are really to further test this neural network. We want to train the neural network in forested areas alone versus open areas and then see how that works. And also to analyze the performance on slope terrains, because if you're interested in mountains, then that's where the snow always happens. And so looking at slope terrains. And then also to kind of figure out if we can leverage other data sets like Landsat, where there's a larger amount of bands available, right? But I think the one thing that really interests me is, can we consider using a lot of the algorithms that are pre-canned in Amazon SageMaker and compare that to RoboSat? So RoboSat's essentially an image segmentation model, and SageMaker has an inbuilt one, which we will be looking at testing. And then, so this project really is not limited to working with understanding spring flowering, but it can be scaled out to understanding everything from like water resources to the snow albedo feedback and how that ties back into climate. And the way we have built our pipeline in AWS is keeping that scalability and that flexibility in the back of our mind. And working with ESIP has been great because they have kind of spearheaded, given us that mini grant to work on a startup project. And we are just going to plow straight ahead, and we have this great pipeline built up. And so with that, I'm going to hand it back to Annie.
Thank you, Amanda. All right. So I hope you see what is, well, I mean, you have to have incredibly capable PIs and co-Is on your projects that make, I think these two individuals in their projects are really interesting. I also think that the spirit of the development is not only to have, I mean, and it'll be great that we'll have this entire package of the project, but I hope you were able to see that each of those projects have a lot of smaller components that could be potentially reused. Just the quality control bit of that Matt showed within his data of those JSON-LD files, the ingestion of planet data, that within these ESIP lab projects that we hope to find things that have a lot of reusable parts that could be of value to the earth science community. And so I guess my last kind of message to all of you is around the idea of community and experimentation. You know, AWS certainly provides the compute, but for earth scientists to fully take advantage of what will soon be available, they need to be able to navigate this environment. We don't want to enter a paradigm where there are the cans and can'ts in terms of utilizing this data, where you have researchers at some institutions that are super cloud savvy and others that aren't. And if you're not in the earth sciences and you're in finance or in disaster response or healthcare, I encourage you to set up the kind of community resources where you're empowering the people that you deal with to kind of play, to get in, to create prototypes, then to expose them to your community so they could provide feedback and let them know if they'd be valuable. And this is at least our approach to hopefully creating a kind of next generation, not even just next generation, but sage scientists that are able to make this transition and fully take advantage of kind of what is ahead of us in terms of cloud computing and the earth science data that will be available. I have this image up. ESIP is a community that meets in person. We meet twice a year in person and virtually. Our next meeting is going to be in sunny Tacoma in July. And with that, I'll say thank you to Matt and Amanda. And again, they're a part of teams that did these projects. And I would encourage any questions or anyone to come up and chat with us after if you have questions both about the community infrastructure that is ESIP or about the specific technologies that they presented in their projects. So thank you, everyone. Does anyone have any questions? Yeah. Yeah, right over there.
How competitive is the grant application process? Can you talk more about what you're looking for?
Sure.
Apply, who's eligible to apply?
Yeah, absolutely. So we put out 2 requests for proposals every year. And the qualifications are someone on your team, a co-I on the project, has to belong to an ESIP member organization, which isn't that hard. There's 140 now ESIP member organizations. We have members in most federal agencies. And so you have to have a co-I. That's part of our member organization. We look for proposals, again, that are collaborative. If it's everyone is in the same kind of domain, those aren't as competitive as those that are working across different domains, and that can even just be computer science and a domain science. Not a lot of, we're still kind of spreading the word about this process. It's very well known within our community, but not as much others. Sometimes we have 15 applications for 5 spots, and other times we have 6 applications for 5 spots. But every year we support about 10 projects. Any other questions?
If you
Yeah.
do have additional questions, there's a microphone in the middle of the room, so we could capture that.
Oh, yeah, there's a mic back there if anyone wants to go ahead.
Thank you.
Great presentation. Sorry I arrived late. I would like to know where you get the data for the figure basically from the Earth. My second question is why you choose PyTorch instead of TensorFlow?
Chose what, pardon me?
PyTorch instead of
Oh.
TensorFlow.
So was the question, where are they getting the Earth observation data and why PyTorch? Yeah.
So here we go. The data, I'm assuming you meant the Planet Labs data. So we are called something like Planet Ambassadors, and you can sign up for that, and you get actually unlimited access to Planet data. It's like planetdata.com. And yeah, so we have that going with them. And then also your question about PyTorch. I don't know if we're using PyTorch. We're using RoboSat, so I don't know if that helps answer your question. Okay, all right, good catch. But we're using RoboSat, which I think has some like PyTorchy stuff in the back end. So yeah, okay.
Any other?
Thank you for the great presentation. I am interested in the weather forecasting models. Have you done any work in that front, or is there a vision moving towards that goal?
So ESIP, as a community organization, we do no weather forecasting. Our members do. NOAA is one of our sponsoring agencies, and I can guarantee you, I'm sure there are maybe some NOAA folks here, that they are doing weather forecasting. All right, yay NOAA. But again, I think one of the reasons that NOAA and other federal agencies find value is because even within weather forecasting models, they're dealing with real-time streaming data, they're dealing with data from multiple sources, and so collaborating with their fellow data folks is really important to ensure those models are accurate and adequately disseminated to the public.
Great, thanks.
Mm-hmm.
To what extent is the work that ESIP is doing is internationally focused versus US, both in terms of grants as well as in terms of members?
Sure, yeah, the question was about if ESIP is US focused. Primarily, our kind of genesis was 20 years ago when the NASA Earth Systems ESDIS, Earth System, I guess, I'm not going to remember it on the stage right now, but we're looking for public comment on the development of their Earth science data systems. So the genesis was kind of out of the public data sector. We are starting something called E2SIP in Australia. I'm sure a lot of you have heard the Australians are also really forward thinking in their Earth science data systems and have been eager for kind of a community organization similar to ESIP, so that is currently kicking off. We have members that participate, quite a few in the semantic technologies community in Europe, but people that we fund, you have to be eligible to work in the United States, and our primary focus, I would say, is within the United States. Any other questions? All right, great. Well, thank you so much. Enjoy the rest of your conference.